Hello everyone, this is Trip Johnson, and this is Lab 4 of Physics 2211 at Georgia Tech. This lab will discuss oscillations. The purposes of this lab are to extract and interpret data from a weight swinging in an arc connected by an oscillating spring, and to use the energy principle to calculate changes in position and velocity. Something that we will figure out in this lab is that it is a very difficult thing to monitor accurately. The premise of the experiment is that a metal weight is hung from a spring, is pulled by a hand, and released as the video shows. This creates a complex path of travel that swings both left and right and up and down, creating a two-dimensional oscillation. For this experiment's calculations, we will need to account for different energies, which in this case will be kinetic energy, K, gravitational potential energy, UG, and spring potential energy, US. Before we continue with calculations, we first need to establish the key assumptions of the experiment. We are setting our system to be the spring and the weight, and our surroundings are going to be nothing, so that energy is conserved within the system. Therefore, the only forces acting within the system are going to be gravity and the spring. The relevant equations to these energies are delta K equals 1/2 mv squared. The force of the spring is equal to the spring constant times the stretch, and work is the force times the displacement. Now that we have our system, surroundings, and equations, let's get to some calculating. Let's define some variables. The experiment is happening on Earth, which means that the gravity will accelerate objects at 9.8 meters per second towards its surface. We are given some variables as well coming into the lab, such as the mass being 0.402 kilograms, the spring constant being 6.83 newtons per meter, the relaxed length of the spring being 0.123 meters, and the time step of the video being 1/210th of a second. We use the variables that we are given to perform a looping calculation within a GlowScript program, creating both a predictive model and an analytical model of the tracker data. This tracker data was used by analyzing the video that we showed earlier, and with the data in the computational model, we were able to calculate kinetic energy, gravitational potential energy, spring energy, and the total energy in the system. Now that we have a way of computing the data, let's make some conclusions about our findings. One important question to ask from our computations is whether or not energy is actually conserved. We are able to track total energy using our GlowScript program, and its resulting graph demonstrates in orange that the total energy remained constant across all data points, meaning that energy was in fact conserved. Another important data set to compare is a predicted GlowScript model that we also wrote during the same initial conditions with the real tracker data. As shown by the graphs, both X and Y predictions in blue are similar to the real tracker points in red, but of course not perfect. The difference could have been because of missing frames in the video, rounding within the computational model, or even incorrect starting values. We can also find the period of the X motion and compare it to the period of the motion in the Y direction. In the X direction, the period is estimated to be around 1.6 to 1.67 seconds. When looking at the graph of motion in the Y direction, the period is also estimated to be 1.6 seconds. The periods in the X and Y direction are the same, which means that the path of motion must take some loop, which is evident through the video. Thank you all for watching.